So I figure, let's go ahead and get started with it. So, think back, way back, not just at the beginning of Chapter 4, towards the beginning of the semester, which I know was not actually that long ago, but towards the beginning of the semester, as long ago as it feels, we talked about a few different types of motion. And through the very beginning, we started talking mostly about linear motion. We characterized that. We talked about position. We talked about velocity. We talked about acceleration, those good three things that we've got. And then all the other derivatives down if we really cared about that stuff. But we said for now, we don't. But when I introduced motion in the first place, I talked about how there are multiple different forms of motion that we might be experiencing. We started with linear, but we also saw there was projectile. Today, we're going to be talking about the third in all of those pictures, circular motion. But what was the fourth one? Does anybody remember? A special fourth type of motion that was of the things that we had. Yeah, rotational motion. Rotational motion is different from circular motion, and I tried to highlight that at the time, but I do want to talk about it again now, right? These are different things. So, for example, if a child or some person sits on the merry-go-round, they are going through circular motion. They themselves are moving about one central axis. The merry-go-round, because it's doing the spinning, that would be classified as rotational motion, while the person riding it is going through circular motion because they're going around the outside of it, which might be a little bit confusing, but let's just kind of dive into this one. So as we've been talking about this stuff, right, we started with linear motion, then we moved to two-dimensional motion, but both of those things are not quite what we're talking about today. So these are examples of things that we have seen now, right? This is more of a review than anything else, but these are examples of not circular motion, not even uniform circular motion, specifically, but not circular motion at all. Motion along one axis. Last I checked, a line, still on a razor, a line does not equal a circle. Hopefully we all agree with that. Similarly, if we have some two-dimensional motion, an x and a y, and it's doing something, I don't know, if it looks in a wavy shape like this, also not a circle. If it goes in some sort of parabola shape, like projectile motion, not a circle. None of those things are circles. None of them are actually going to do it for when we're talking about uniform circular motion. But these are still useful things, right? This is all still stuff that we are getting used to using at this point. We have velocity, acceleration, position in R. We can split those up into components, all that good stuff, right? The stuff that we have been doing so far out of Chapter 4. Now, what is uniform circular motion is a picture kind of like this. So there are two parts. The first being circular. You got to be in a circle if you're moving in circular motion, right? That's really the only thing we've got out of that one. But the second one, the uniform part, is referring to the speed at which we are moving around that circle. That is to say, we might notice we're moving in a circle. Fantastic. Excellent, right? We can see that. A trajectory picture would tell us that. What a trajectory picture does not tell us is whether or not we have a constant speed going around that circle. And that's the second very important part. Of course, this is not always going to be the case. We can have a non-constant speed. We can be accelerating. We can be decelerating. We can be doing whatever we want. But there are special equations that apply when we do have uniform circular motion, and that's why we give it its own little bit of emphasis. So, if you have your definitions down pat and you've been working with these things and you feel very comfortable, you might notice that while the speed around this circle is going to be constant, the velocity is certainly not. And the reason for that is the velocity also has a direction associated with it. And as you're going around a circle, you are constantly changing direction. You are never in one direction for any period of time, right? If we were moving in a square, then I could argue, okay, well, you've got a constant velocity at least for a little while. But in a circle, because it's constantly going around, you never have the same velocity as you did in that last instance. But the fact that there is a changing velocity implies that there must be an acceleration. Remember that acceleration might not just be speeding up or slowing down, it can also be a change of direction. But let's get back to that. For now, I want to draw some parallels. When we're talking about circular motion, when we're dealing with these things, of course, if we're going to start talking about movement, the first thing that we talk about is position. So here's how we're going to start describing angular position. Typically, we have been talking about things in terms of x, y, and z. Where is it in space? We draw a graph, we plot out the thing, we do all that good stuff. We have another set of coordinates that's a little bit easier to use when we're dealing with circles, and it's called polar coordinates. Polar coordinates, instead of using x and y, are going to use r and theta, kind of as illustrated on this graph right here. R is your distance away from the center, your radius. Theta is your angle around the circle. So that is anywhere between 0 and 2 pi, right? Because that's a full circle. Once my angle is 2 pi, I'm right back to 0. So to relate some of these things together, to go back and forth between a lot of our descriptions, for one, if we wanted to find r, we, again, have just a triangle, right? So that's a hypotenuse if we have x and y. If we're looking for that angle just in the exact same way, we have a triangle. So inverse tangent, arctangent, same thing, would give us what that angle was as well. One slightly different thing is this arc length. So we're digging up all that old geometry knowledge. Remember that any path around a circle, if we don't go the full way, if we go the full way, that's a circumference. If we don't go the full way, that's what's known as an arc length. So what I've got highlighted in red here is one such example. We start from 0, we go around the angle theta. Once we hit that spot, this portion of the circle, and only this portion, is known as the arc length. And if we wanted that distance, that's going to be r times theta. And then I kind of remind myself of this thing. I don't always remember this one, but what I do remember is that if I go all the way around the circle, if theta is equal to 2 pi, then what I get is 2 pi r, the circumference. Anything less than 2 pi, and that's the length that I get from that. So one thing that I do want to point out here, I was just talking about some sort of arc length. An arc length would be measured, any sort of distance like that. A circumference would be measured in meters, centimeters, inches, a distance, as we're used to working with it. And that's going to remain true. But this angle, how we actually get in there, you might already notice, well, I've already got a length r. What are the units of theta? You may or may not know this one, but theta, as we are going to use it, should always be in units of radians. When we're talking about the difference between radians and degrees in your calculator, we're talking about these radians now for these things. Again, there's a simple conversion to go back and forth between them. They imply the same thing, but radians are their own special unit. Typically, whenever you see pi or theta or anything else like that, it's going to be coming with some sort of unit radians. So watch out for that, and it might be a little bit fuzzy how and where it shows up in some places. But I want you to keep that in mind. So there is essentially an angular position that you might consider theta, but there's also a distance around the circle, arc length, s, and they're slightly different things, right? One of them tells you how far around the circle you've gone. One of them tells you what is your position right now. It's kind of like the difference between distance traveled and displacement. So naturally, as we're talking about these things, you start from position, you go down a derivative step, you end up at velocity. We similarly have velocity, right? But now it's called angular velocity instead of just velocity, or linear velocity if you really want to be specific. It's called angular velocity because it talks about how fast we are going around our circle. So angular velocity represented by this symbol lowercase omega. Right, that is specifically called omega. You probably recognize its big brother, capital Omega. That is not the unit that we're using right now. This curly W looking thing is actually a Greek letter omega. And just like our description of linear velocity, if we take the change of position over the change of time, we get the rate of change of position, right? Velocity. Change of position in angular terms, divided by change of time, gives us change, or the rate of change of angular position, angular velocity. So this means exactly the same thing. Then if you wanted to go to an instantaneous case, all you would need to do is take a derivative, right? Everything that we have seen so far about linear position, velocity, acceleration also applies just as well to the angular stuff, right? All of our relationships, all of our equations, they work almost exactly the same. So, is everyone with me so far? That's a good thing to highlight, but that is something slightly different because omega is exclusively talking about how far around the circle we have gone. Once we bring r into it, now we're talking about real distances. So in order to find angular velocity, this is one way to do it, right? You can either take the derivative sense, or you can take, if you have 2 different points, you can use that as well. Now, one thing that I do want to show here, actually, while I'm talking about this, one of the very, very common examples you're going to see for these things is finals, right? And I do have some right here with me because I am one of those people. But for example, and this final's never as pretty as it was advertised to be. Let's imagine something, right? And I realize I'm going to mishandle this, and anybody that really cares about finals is probably going to scream here. But let's imagine I'm looking at 2 points where each of my index fingers are. Where each of my index fingers are, they're kind of like along the same path from the center, right? When I spin this thing, can we all agree that the distance traveled by the outside finger is much greater than the inside finger? Do we all agree on that as we see this thing? If I move around like this, yeah. There's like a little tiny distance, like here to here for this one, and then this one goes all the way around the outside of the circle. But being attached to the same disk the entire time, it's all rotating at the same rate. And that's the difference between linear velocity, what each finger itself is doing, and the rotation as a whole, which is what our omega represents. The omega doesn't care where you're at on the circle, it just cares about how the circle is rotating around. That's the key difference here. So, and again, people might be screaming with what I'm doing with that thing, but it's fine. It's not a rare record or anything. That's what we're trying to imply here. We can take that a step further, and we can try to relate our linear and our angular values. Right, so for one of these, we can immediately think about that distance traveled, our arc length. If we wanted to know how far around the circle we have gone in meters, if we want to talk about, like, you are at this radius from the center, you travel around this angle, that is what we get as arc length. And that is related of s is equal to r times theta. If we take derivatives of this, right, so if I take a derivative of a position or a displacement, I should find a velocity. Let's do that right on down. Take a velocity of this thing, so ds dt, that's equal to my velocity v. Then I look at these things, and I again think, okay, what happens if I spin around? If there is some change as I spin around, is my radius, is my distance away from the center changing at all? Yes or no? What do we think? As I rotate this thing around. No. Right, we're still on the edge of this thing, right? I've pinched this thing right on the side here, so I'm not going anywhere with this. But as I rotate around, that theta is changing. I stay on the same distance away from the center, so that's a constant. The time derivative skips right on by that thing, but since theta is changing, it gets stuck on that one. We know from the last slide here that omega, our angular velocity, is d theta dt, so that's where we get this expression that the tangential velocity, or linear velocity, is equal to r times omega. It's a nice little relationship together. Omega is not a full circle. Omega is only our angular velocity as we go around the circle, the rate at which we go around the circle. One other value that we have when we're talking about the relationship between these two is when we talk about one full rotation. So the time it takes to complete one full rotation is known as the period, and there's a few different ways that you could talk about that one. For one, you could say, hey, it's the circumference, a distance, divided by my velocity, meters per second, right? So meters divided by meters per second, that feeds out some sort of time in seconds. Or I could just say, hey, once I move the full 2 pi, I've got my full rotation. So that's 2 pi radians divided by omega in radians per second gives you the exact same seconds at the end of the day. So let's go ahead and try this in a problem. And this is not so much of a problem as it is just kind of converting between some units. So I keep talking about omega being in radians per second, right? I keep mentioning that, radians per second, radians per second, radians per second. However, omega is always just going to be some measure of how quickly are we rotating around the circle. So technically, don't take this too far out of context, technically, 45 rotations per minute, RPM, is a unit, a possible unit of omega, angular velocity, because it tells us about those rotations and how long it takes to make those rotations. It's a very common unit to see. I see RPM in everything, right? Typically, that is the de facto unit for when you're talking about something spinning around, but it's not a common unit that meshes well with things like meters and newtons and kilograms. So most of the time, we will prefer things to be in radians per second, even though an industry standard is RPM. So here's your first exercise, trying to communicate between the two. Old single song vinyl records would rotate at 45 RPM. And I realize there's a top and a bottom for those things, but whatever. 45 RPM. Well, what I want you to do is first find the angular velocity in radians per second, not in RPM. Second, find the period of rotation in seconds. How many seconds does it take to make a full, complete rotation around on this thing? So I'm going to say take the next 4 or 5 minutes, give these a go, try to convert through these units, and then let's come back together and see what you got. Canvas will freak out. I think Canvas will probably freak out if you try to put it in pi. So make sure to put in the actual number from it. And speaking of, let's go ahead and start taking a look at this thing as we've got it. So here's what I'm thinking. We've got this thing spinning around in some way or another. But what we're really given here is that this thing is spinning at a rate of 45 RPM. I'm just telling you that RPM is not really a useful unit. (45 RPM). So there's a few different ways that I can think about these rotations, right? And that is an important point that I do want to bring up here. When we're talking about one rotation, what goes on in one rotation? The time for this when we're talking about a single rotation, the time it takes, we give it a special name, capital T, called the period. We can also say that one rotation has a change of angle, change of theta, equal to 2 pi. Right? Those are two big important things that we should probably have when we're talking about this. But we also should be looking here as to what's going on with this thing. So when I'm talking about this change of theta, 2 pi, this is specifically 2 pi radians. That's the unit that I'm using here. So when I'm trying to do this conversion, let me write it out like this. Omega is equal to 45, and I'm not going to write RPM. I'm going to actually write out rotations per minute. To convert to radians per second, we need to convert both of these units. So what I could say is that, okay, well, there are 2 pi radians, 2 pi rad per rotation, one rotation. So that would cancel out my unit of rotation. Now I need to cancel out my unit of minutes. I would say there is 1 minute per 60 seconds. That will safely eliminate my unit of minutes. Now what I'm doing is I'm multiplying across. 45 times 2 pi divided by 60. Plug it all in together, and we should end up at a value of 4.71 radians per second. Of course, I am cutting off some decimal points here because pi is an irrational number and has an infinite number of decimals attached to it. But I I don't know, I want to keep my sanity. I feel like trying to solve pi is kind of like looking into eldritch horrors. You're just going to lose your own sanity doing it. 4.71 will work if you're talking about this thing for Canvas. You do want to make sure that you put in a number for this thing. Don't try to have any sort of multiple of pi. It won't know what to do with it. And then whatever value it's got a little bit of range on it. So you should be fine with whatever you want to put in. Now, the second part of this is asking what is the period of this rotation? And I can actually imagine a couple different ways to do this one, depending on what values we have to start with. So one of the ways that I can imagine doing this thing without using any of the values that I just solved for, so when we're talking about this period, one of the ways that I can imagine this thing is I could say, hey, this is how long it takes to go around the rotation, one rotation, and I'm dividing this by my 45 rotations per minute. And the reason that I'm doing this is because we notice this is my how much have I rotated divided by how long has it taken me to rotate. These are not standard units. They're not radians. They're not radians per second. There's nothing like that. But they do share common units between themselves. And in doing that, the rotations portion cancels out. So what I get here is 0.02222222222, a few more if you really want it, minutes. Which is fantastic on its own, but it is not our standard unit of seconds. We would like this thing to be in seconds. So I do one last conversion here, multiply it by 60 to get 1.33, again continuing, seconds. This is one way to think about this, and maybe this is not the way that you approached this. The other way that you might consider approaching this is to use one of our brand new equations that we just got. I have given you the equation that the period is equal to 2 pi divided by omega. That is a full rotation of the circle divided by how fast we are rotating around the circle. Notice it's really the same thing as up here. Right? They're kind of saying the same thing. One just has standard units rather than rotations and rotations per minute like what we have. So plugging in those values, 2 pi divided by omega, as I have just found it, 4.71, would give me the exact same expression, 1.33 seconds. And yes, the 0.022 to 1.33, that is the conversion from minutes to seconds. Two pi r divided by v. So that is our 2 pi divided by omega right here. Yes. But that's going into that expression. The other one that we would possibly have is 2 pi r divided by v. But since we don't have v, this one's not going to be super useful for us. Not unless we find v first, but that's another step just to get back to what is essentially this expression. All right. So let's go ahead and keep talking about some things. What is that acceleration that I was talking about, right? I kind of glossed over that. We said, hey, there has to be acceleration. Where was that? All the way back up here. I said, hey, there has to be acceleration. And then I said, but that's a surprise tool that'll help us later, right? We didn't actually talk about it. Let's actually talk about this thing now. Now that we have established what polar coordinates are, I want to specify that there's a couple different ways that you can think about direction here. And let's imagine for a minute. I'm going to draw this in, what's a good color that stands out? Let's draw this in red. Now, let's do it in like this hot pink magenta color. So it really sticks out. Let's imagine that we were doing this in Cartesian coordinates and that I could draw straight lines. Y and X. Let's look at our acceleration as we go through with this thing. Let's look at this r hat. We have to imagine that if we were right here, and our velocity, we're going to the next step here, our acceleration has to be pointing inwards towards the middle of the circle. Okay, well then, r hat has a positive x and negative y. And then a little bit later, I look at this one, and I would say, okay, well now it has a positive x, positive y. And then I look a little bit later, and now it's got a negative x, but a positive y. And this is getting confusing, right? I don't want to deal with it like this. If the direction of my acceleration is constantly changing, I'm probably not going to have a very fun time solving out what's actually happening. Because it's not even that it stays in that direction for a little while, it is constantly changing because it's constantly moving around the circle. So instead what I'm going to do is I'm going to come up with some other directions that might make this a little bit more useful. Specifically talking here, I'm talking about r hat and t hat. And remember that anytime we see that little hat symbol above, that means it is a unit vector. And a unit vector always has two features. And what are those two features? Or I guess two things about it, two very important things about unit vectors. They always, always, always have length 1. And what are they trying to imply? What are they telling us about? They tell us what direction things are going. So length 1 and direction, they are not trying to modify the magnitude at all. Their entire point is that they are the multiplicative identity, right? Which is a very fancy way of saying it's multiplying by 1. It doesn't do anything. But it does tell us what the direction is. So when I'm talking about this acceleration is much easier described if I say acceleration is always pointing in the r hat direction. That is, centripetal acceleration points towards the middle always. Here, and here, and here, and here, it's always pointing towards the middle. So that way, our direction is not constantly changing according to our unit vectors. Our unit vectors are changing constantly, but that's actually a lot easier to deal with than if we were trying to think about this in terms of x and y the entire time. So let's get rid of these x's and y's. Now, the other thing that we can do with that is that, okay, well, that's where our acceleration is going, but our velocity is not pointing in that direction. And you would be correct in saying that. Our velocity points in the t hat direction, and it's got a t with it because it is the tangential direction. It's going along the outside of the circle the entire time, right? Going along the outside of the circle like that, we've got tangential, velocity, acceleration, whatever we want to have with that. It is also constantly changing, but notice that these two are always perpendicular with each other. And this just makes the whole thing a lot easier to talk about, it turns out. So the big thing that we're looking for in this thing is this equation right here. Acceleration, the acceleration that keeps us in the circle, centripetal acceleration, is equal to v squared divided by r, which is a little bit strange at first. And there's some nuance to this equation that is not going to be super clear until we start getting into forces. But what this is saying is this is the necessary acceleration to make sure that we stay in a circle for a given speed. That is, imagine some engineers, and this is currently something that's happening. We're planning the next set of GPS satellites. We have an idea of what altitude we want them to be at. We also have an idea of what Earth's acceleration is at that altitude. If we put them up at the wrong speed, they'll burn up in Earth's atmosphere. If we make them too fast, they'll fly out into space and be useless for us. We want them so that they're perfectly rotating around in a nice circle with very, very, very minimal adjustments. So what we would do is we would say, we know that acceleration. We know that radius that we want to put it at. We need to find then, or we can calculate, what velocity, what speed we would have to put them up there at to make sure they stay in that perfect circle. Any changes to that, and we get circular-like motion, it's still spinning around, but it's either spinning around down or it's spinning around out. Neither of those are very useful for commercial satellites. But I'm going to hit on that one a little bit later when we actually get the chance to talk about stuff like centripetal force, because I'll have some better things to say then. For now, I've got another problem for you. So let's imagine, I know this is not the case, but let's imagine that Earth rotates around the sun in a perfect circle. This is so much easier to deal with than an ellipse. I promise you don't want to bother with an ellipse. Let's just pretend it's a circle and be done with it. But if it were rotating around in a circle, then it would have a radius of 1.5 times 10 to the 11th meters, right? A pretty big distance. What I want you to find, and let me talk about these units. I want you to find the velocity, tangential velocity specifically, in meters per second. I'm interested in the angular velocity in radians per second. And I'm interested in the centripetal acceleration in meters per second squared, because technically speaking, I could immediately just say, oh, angular velocity, 1 rotation every year. Did it. I'm not taking that this time. Convert this into our standard units as we would use them. And then we'll have our 3 parts to this. So because we've got multiple parts going into this one, and this is a little bit more unit conversion and everything else, I want you to take the next 6 or 7 minutes to work on this one. And then we will all come back together and see what you got. All right, how's about we start taking a look then? So first thing I want to do here is I would love to draw a picture. And let's draw I don't know, not a fantastic one. It doesn't have to be great, but good enough. So we are going to move in some sort of path like this. And admittedly, there was, we got a little bit of information in this problem, right? But not actually a ton of information because we only got the radius, right? Isn't there more to it than just that? Isn't there more details that we might be interested in knowing to actually solve this thing? But we're dealing with Earth. Right? We know some things about Earth. Maybe not a ton, but we know some things about Earth. Namely speaking here, how long does it take to rotate around the sun? One year. 365 days. Whatever number. I should know this better. For anyone that actually likes theater and everything else, there is an actor named Anthony Rapp that sang a song about how long a year is in seconds or something. I don't know. I don't like musicals. Yeah, that's the one. I don't know it nearly as well. So let's draw Earth then. And we know it's all Ohio. Something like this. That's kind of like Ohio, right? There's Earth. And I feel it is very important. I mentioned this in the last lecture, but I'm going to mention it in this one. This is a joke. I do not believe in a flat Earth. We just have a strange fascination with them in the physics department here. We have kind of been interested in them for some time after somebody did a project and actually got into the society and was looking at a lot of the videos and everything else. One of my friends. So, jokes aside, let's actually talk about what we've got here. We're really only given 2 values, and we're asked to solve a few different things based on that. We are given that the radius, first, is 1.5 times 10 to the 11th. And that is measured in meters, an important unit. But we also know that the period of this rotation is 1 year. And I'm just going to use 365 days. And yes, all Ohio. We're asked to find 3 different things. The tangential velocity, the angular velocity, the centripetal acceleration. Ohio is mostly flat. Granted, I don't believe in East Ohio, so I don't even know that I trust in this half. I've had a strong feeling for a long time. I don't think East Ohio is a real place. So, as we have these different things, we have different pieces that we might use to solve for this thing, but I'm actually going to start with omega because that actually is going to be my least intensive one. See, I can take this relationship between the period and the year, and first what I should do is I should actually do that conversion. I don't want this in years because years are not standard units. What I'm going to do is I'm going to convert this into 31,536,000. Drawing some commas in there to make sure that I can actually keep track of what the units I have. If you are from some other place that uses commas as decimal points, I'm so sorry, but I'm not going to change it. I know it's backwards between some places use commas for the decimal points. We use periods for the decimal points. Whatever a mess that is. But anyways, I can just solve immediately out for omega. I can say that the period t is equal to 2 pi divided by omega. My period, if I use the seconds, pi is radians. So I'm already in everything that I need for standard units. Rearrange this thing. Omega is equal to 2 pi divided by the period. That is, a full rotation divided by how many seconds it took to make that full rotation gives me radians per second. Here, that is 1.99 times 10 to the negative 7th. Which is small, right? Compare that to what we just saw. 1.99 times 10 to the negative 7th versus, for this other one, we had 4.71 flat, 4.71, right? But think about this, is that the rotation, how long it actually takes to go around, it's 1 full year to make one complete rotation. It's not a quick rotation. So the amount that we actually move on a day-to-day basis is very, very small. Remember that t here is the period of rotation, how long it takes to complete one rotation. But that's our first value, and I know I skipped over v, so let's go back to that. Now we're looking for tangential velocity. How fast is it moving? It's kind of like this, right? At this moment in time, going around the circle, that is our tangential velocity. Tangential velocity, probably the easiest way to write this one out is going to be 2 pi r divided by t. Just in the same way that I could say that period is equal to 2 pi r divided by v. Rearrange this. V is equal to 2 pi r divided by t. Doing so finds a velocity of 29,886 meters per second. Pretty fast. T is always in a time value because it is specifically a time, an amount of time to complete one full rotation. So whether that's a year, a day, in seconds, whatever value it's in, it is always specifically a time. The other way that I could have done this is I could have taken this value omega that I just found, or I could have said v is equal to r times omega, and that would have gotten me the exact same value. Right? Either of those would work. It's just the second option means that I have to have already calculated and correctly calculated omega. And if I have the chance to avoid reusing values that I may or may not have gotten correct because accidents happen sometimes, I'm probably going to take the one that depends only on the given variables. We can absolutely use v is equal to r times omega. And props for getting the proper omega symbol in chat. You're either very fast with the different expressions or you know those alt codes very well. Would I have to convert units if I went that route? No, not if omega is already in radians per second. Not if it's already in radians per second. If it's in radians per second, then it's already covered. It's in a standard unit. You'll keep everything in standard units the entire time. So the very last one that we've got, again, I'm going to use standard units. My centripetal acceleration, v squared divided by r, meters per second squared, the whole thing squared, divided by meters, is going to spit out a value of 0.00595 meters per second squared, our standard unit for acceleration. Omega is, I love omega. Omega is one of my favorite symbols, but I also have dealt with all sorts of optics things. There's acceleration. I just stole my value from v that I found, divided by, v squared divided by r is all I've got for that one. That's the expression that we've got. That is a relationship for centripetal acceleration. Absolutely. The value that we've got, the 1.5 times 10 to the 11th, is our radius. That's this value. So So, and let me try to write this out better, because as we've got it, the tangential velocity is a straight line coming off of this thing. Whereas, so it's a straight line kind of going, again, tangent to the circle, because that's what it means to be tangential velocity. So here's our velocity v, whereas omega spins around like this, goes around the circle. Try and get, I'll just zoom out a little bit, get everything on there. Well, I do want to talk about one last case, and you will have hopefully encountered this in your reading, but it's not necessarily something we're going to harp on too much quite yet, but maybe a little bit. But in the case of non-uniform circular motion. So I keep talking about these parallels between linear motion and circular motion, and for the minute, let's just kind of ignore that this is here. Let me scribble this thing out, and I'll come back to that. We have gone through each of these steps to talk about how there is a relationship between the two. Between all of these things, if I have some sort of position or some sort of arc length, if we would like to do that, there is a parallel in circular, but it's in theta. If we wanted to talk about a tangential or a linear velocity, then that is the rate of change of our position. Just in the exact same way is omega the rate of change of theta. To go back and forth between linear and circular, you might notice that all you actually need to do is multiply by r. That's one of the really cool things about this. If I take theta times r, I actually get back to my distance in meters x. If I take my angular velocity and multiply it by r, I get back to my tangential velocity. We can look back at our equations and find that. V is equal to r omega, s is equal to r theta. That's the relationship between circular things and linear things. It's a really easy relationship, and all of the things you have learned so far about acceleration, velocity, position, any of those relationships, they hold true for circular motion because everything's parallel. Now, the last bit that I have covered up here is I have been talking about uniform circular motion. There is the case of non-uniform circular motion where we have an acceleration alpha, not a, but alpha, to give it, a little bit of a difference here. But alpha is specifically a tangential acceleration. So if we were talking about this thing going on here, we have, if I want to take this object, for example, let's take this one and let's draw that my acceleration A, centripetal acceleration might point in this direction, but a tangential acceleration would point in T. That would be alpha instead. We're not going to see a ton of things with this quite yet, because realistically, this is going to become a much more important topic in a little bit later once we've talked about energy and momentum a little bit more. Then we can hit this a little bit harder and see some of the really cool things. We might talk about it a little bit, but not a ton quite yet. But while we're here introducing circular motion, I thought it was worth mentioning, worth going over a little bit, especially because the book does as well. So, but just in that exact same way, we don't have it quite yet, but there is not quite the same relationship between these two. There is some relationships that you can draw between them, but this one has a little bit more of a break in between them. There are some differences, some nuance to that you can't quite go back and forth between them. But for velocity and position, you absolutely can. They are exactly parallel, and even in the same way. Our acceleration's a little bit different, but for the most part, it's got all those same similarities that we've seen before. So, that's actually all I've got for today. We're ending this one a little bit early. There's, I don't think, a huge point to diving into forces quite yet. I'm happy to just call it here early for a little while. Earth's acceleration in that circle, 0.00595 meters per second squared. But next time we're going to start diving into forces a little bit more, talk about some of those fun things. I know you've got a little bit of a longer reading before the next one, and those questions will be out here very soon. But talking about forces is really, essentially, we've been talking about moving things. Now we're going to start getting into why do they move. Not how do they move, but why. But that's it. That's all I've got for now.